Okay, so for 6.8 applications of exponential growth and decay, we remember these two formulas from yesterday's lesson. Um, we're going to talk about the parts again, just a little bit differently. So again, we're going to start off with the a value here. The a value represents the initial value. Previously, we've been calling this the y-intercept, which it is, but we're going to refer to it as initial value for the purposes of our application problems. If you recall from yesterday, we have exponential growth and exponential decay. They're determined by whether we have 1 plus our rate or 1 minus our rate. Our rate is this growth slash decay rate. And we are going to plug it into our formula as a decimal. But oftentimes, when you are looking at a word problem, you're going to see it as a percent. Our answers about rate should always be in percents. Now, the two kind of different things that we're going to see when we start talking about these application problems is that x is going to represent time, x is our exponent in our equations, and y is going to represent our future amount. So we are going to be making some kind of predictions using these formulas. If I take a look at number one, in a small town in 1985, there were 285 cell phone subscribers. The number of subscribers increased by 75% each year after 1985. So the first thing I'm seeing right now is that we are saying that our number of subscribers increased. That means that I'm looking at exponential growth. So I'm going to be using this first formula here. When we look at letter A and it says write an exponential equation where x is years since 1985 and y is the number of subscribers, I'm just writing my equation. I'm not plugging anything in yet. I just want an equation with x and y values in it. So to start off, my y value is just going to be y equals. Then I go to my initial value. My initial value says that there was 285 cell phone subscribers. So that is going to go in the position of A. Then I do 1 plus, because I'm talking about exponential growth. And then I'm going to look for my rate. My rate is 75%, but we want to convert that to a decimal. To do that, I move my decimal place over 2 spaces to the left, or you can multiply or divide this by 100. That is 0.75. Then we're going to finish it off by putting our x up here in the exponent. Now we can go one step further by simplifying this the center down. So 285, and then instead of 1 plus 0.75, we'll make this 1.75 to the x power. And that's our simplified equation. Now in part B, it asks how many cell phone subscribers were in the town in 1994. So we're being asked to predict the total number, our future amount, if the year is 1984. So I'm going to rewrite my equation. I don't know what y is. That's what I'm about to figure out. And then I have the rest of my equation, 285 times 1.75 raised to the x power. Now, if you remember, x represents time. X specifically in this problem is years since 1985. So I'm going to do a little quick math here. 1994 minus 1985 gets me that there is a 9 years difference. So my exponent is going to be a 9. Now, all I have to do with this equation, now that it's written, is plug it into my formula. So I'm going to go ahead and open up my calculator here. And you can do this if you have the TI-30XS as well. I'm going to write the entire thing just like that. So 285, parentheses, 1.75, raised to the 9th power. I have, I did not raise that to the 9th power. Raised to the 9th power, there we go. 43,871.986. I'm going to go ahead and figure out what I need to round to when I look at my problem. It says how many cell phone subscribers, so we're talking about people. So if I get a value that's about 43,871.99, I want to make sure that I'm rounding up to the nearest whole number subscriber. So y equals 43,872 subscribers. We're going to include that unit in our answer. Perfect. Let's do another one. So again, we're going to take a look at writing our equation first. So starting with y equals. Toby Flenderson is buying a car for $25,000, so that's our initial value. It's telling me that the car is depreciating in value. Depreciates is a word that we use when we talk about exponential decay. So I know this is going to be 1 minus. Our rate is 7%, so as a decimal, 0.07. And we're going to raise that to the x power. If I wanted to simplify that one step, I would rewrite it as y equals 25,000 times 0.93 to the x power. Now I'm going to take that formula. I'm figuring out what is the value of the car in 2022. Years since 2014, I'm going to do 2022 minus 2014. And that's going to give me 8 years. So when I plug in my formula, y equals 25,000 times 0.93, all raised to the 8th power. Let's go back to our calculator. If you do not have the TI-30XS and you are not able to type all of your equations in one row, here's how we're going to do it without having to round. So I'm going to do some order of operations where I'm going to take my parentheses first, which inside my parentheses is 0.93. I'm going to raise that to the 8th power. And then, because of PEMDAS, after I do exponents, I'm going to do the multiplication. So now I'm going to multiply that by 25,000. Without clearing my calculator, it should get me the answer 13,989.545. Because we're talking about money and we're talking about the value of his car, we should leave 2 decimal places. So I'm going to round up to 0.55. I'm going to put a dollar sign because I need a unit. And there's my answer. Let's do one more like this. Let's do Jim Halpert bought a house for $182,000 in 2008. The property value is increasing, so I know that's exponential growth. So let's start our equation with y equals. My initial starting value that he bought his house for was $182,000. This is growth, so I want 1 plus. And my rate is 5.6. If I move that decimal place over, I get 0.056. And I'm going to raise that to the x power. To simplify, 182,000 times 1.056, all raised to the x power. Now, if I take a look at letter B, what will the value of the house be in 2024? X is the number of years since 2008. So 2024 minus 2008. I'm going to get 16 years. So my equation, y equals 182,000 times 1.056 raised to the 16th power. 182,000 times 1.056, all raised to the 16th power. Again, we're talking about money here, so I want to make sure that I'm rounding to 2 decimal places. This time I have 0.203, which means I'm just going to truncate to 0.20. Dollar sign, $435,205.20. Awesome. You can try number 4 on your own. In number 5, you're coming up with your own scenario for the following equation. So you want to figure out what does your initial value represent. Obviously, this is going to be a case of something decreasing because we have a b value that is less than 1. Our rate here, this is a good review from yesterday's lesson. Our rate here is actually going to be 1 minus something. 1 minus something gets us 0.85. That's going to be 0.15. So our rate, if I convert that to a decimal, should be 15%. And then I don't know how many years. So you want to come up with a scenario where your initial value is 14,000 and you're decreasing by a rate of 15%. I think you can come up with something creative. Lastly, number 6, during the COVID-19 pandemic, why did experts use an exponential model to describe how cases would increase rather than a linear model? Use complete sentences. I would answer this as cases increased rapidly and the speed at which people were infected increased, so it was better than a linear model. If I was talking about a linear model, it would be as if my cases were growing steady over time. However, when we talk about COVID-19 and the spread of disease, our models usually look more like this exponential growth. All right, that's it for this lesson.